We're going to run through a couple calculations to help you better understand what variance and standard deviation represent and how they're related. When we need to know these numbers in later activities, we'll use Excel to do the calculations. To calculate the variance, we want to measure the distance of each point in our dataset from our mean. Intuitively, you might then think to add all these distances together and take the average. Let's try that. Here are our data points. We'll take each data point and subtract the mean from it. Next, we'll add those together. We get 0. Okay, so we have an issue. Some of our samples are negative and some are positive. This is causing our negative and positive samples to just cancel each other out. For that reason, we insert an extra step of squaring each number. Now all our numbers are positive. We'll then take the sum of these numbers and divide by the number of points we have minus 1. This is our variance, represented by a lowercase sigma squared. Once we've calculated our variance, finding our standard deviation is easy. The standard deviation equals the square root of our variance and is represented by a lowercase sigma. Sometimes it is even referred to as the sigma. Often you'll see the variance written simply as the standard deviation squared. If we square our standard deviation, we get right back to our variance. We've learned methods for describing the central tendency of our data and the spread of our data. Let's look at ways to describe the shape of our data. Remember this chart of apple weights? These weights are what we call normal distributed, also known as the Gaussian distribution. The normal distribution shows up a lot. Heights, blood pressure, and IQ all follow a normal distribution like our apples did. The key features are that it is symmetrical around the mean. The mean, median, and mode are all the same, and our normal distribution also has tails on both sides, which approach but never touch the x-axis. Finally, by applying the empirical rule to any normal distribution, we can determine the proportion of values that fall into certain ranges of the mean. 68% of our points fall within one standard deviation, 95% within 2, and 99.7% within 3. We're going to be seeing a lot of the normal distribution. This is because a lot of statistical tests require that our data is normally distributed. This may sound like a big limitation, but it really isn't. We'll explore why in Chapter 3 when we discuss the central limit theorem. Data also comes in distributions that are not normal. It can be bimodal, parabolic, flat, asymmetric, or just about anything. Asymmetric data distributions are common and are often described in terms of skewness. Skewness describes where the data is clumped and where the outliers tend to occur at. With negatively skewed distributions, most of the outliers tend to be on the left of the mean, pointing in the negative direction, while most of the data tends to be clumped to the right of the mean. With positively skewed distributions, the outliers tend to be on the right of the mean, with data clumped on the left. Kurtosis is another description, which focuses on the weight in the tails and around the mean. More or less normal distributions are mesokurtic. In platykurtic, the weight of the distribution is spread around the mean, with very little distribution in the tails. And leptokurtic distributions are more peaked, with very fat tails, and therefore a larger number of outliers as well. While the normal distribution is quite normal, non-normal distributions are also common. In finance, the distribution of asset returns are normally not normal. The S&P 500, for example, tends to be leptokurtic. Real estate, bonds, and commodities and other investments, which rarely swing, tend to be platykurtic. That meeting with the CEO is coming up. You've been poring over the data and pulled a few high-level descriptive stats, But as you dig deeper into the sales data, you're having trouble seeing the trends in the numbers. Don't worry, data visualizations are here to help. We often think of data visualizations as being for our audience, but effective data visualization can help us analyze and reason. Before we begin, there are a lot of different styles of visualizations. We're going to cover just a few used heavily in our first statistics courses: line charts, bar charts, histograms, box and whisker charts, and scatter plots. Line plots typically show a time series. The series you see now happens to be the price of Tesla shares from 2019. With these charts, the x-axis tends to be the independent variable. That is, the variable whose value doesn't depend on anything else. This is almost always a measurement of time. Time doesn't change based on the price of Tesla, making it an independent variable. On the y-axis, you'll typically place your dependent variable, a variable whose value is dependent on the independent variable. Our price does depend on the date. Bar charts are helpful for displaying a variable across different categories. Now, those categories can be chunks of time, as shown here, where Tesla 3 production is chunked across different quarters. Since quarters have a natural progression, it does sort of create the sense of a time series like in our line plot, but the bar chart can work well when our categories have no natural progression. Consider this chart of the number of models produced by color. This method helps us to identify both the quantity and ratio. Histogram is similar to a bar chart. It provides an approximate representation of the distribution of a dataset. To create a histogram, data is put into bins. In this example, returns that are between 0 and 2% are being lumped into one bin and 2 to 4% in another. We've essentially created categories for our numbers based on ranges. You can see a bit of a positive skew in this chart of Tesla returns in 2019. They were having a bit of a run that year. Box and whisker charts shows us quartiles, but in graph form. In this case, we are shown daily gains of Tesla in 2019. We see the gains for H1 and H2. The median is represented by the horizontal line in the middle of the box. Sometimes the average is indicated by an X. The whiskers show us any extremes of our total range, while outliers that we may not have included are shown as dots lying outside that range. Each dot represents a single observation. They're a bit funny looking, but box and whiskers charts convey a lot of information in a very small space. You see the central tendency, range, and you even get a sense of the shape of the data. Its small size makes it great for when we have a lot of distributions which we want to compare. Finally, let's have a look at scatter plots. Scatter plots are useful for visualizing correlations or relationships between quantitative variables. When there is no correlation, the scatter appears a bit like a cloud. Correlations can be positive or negative, strong or weak, exponential, and more. Sometimes you'll see a regression line drawn through the middle. A regression line is a straight line that lies as close as possible to every point in the scatter plot. Okay, those are the 5 visualizations you'll want to be familiar with. Line charts and bar graphs are great for visualizing our descriptive statistics, like your sales data. Meanwhile, histograms, scatter plots, and box and whiskers are going to be useful as we move into inferential statistics and want to visualize differences, correlations, and distributions.